Good evening to everyone. This is my next tutorial class on Maxwell's equation. Here I will discuss some numerical problems, some important numerical problems related to Maxwell's equation. Let us consider the first problem. Electric field at a point R is given. E vector equals to q by 4 pi epsilon naught r vector by lambda r square plus r vector by r cube into exponential of minus r by lambda, where lambda is a constant. This is given. Find the charge density. Charge density is to be calculated. So to find out charge density, let us start with differential form of Gauss's law. This is the differential form of Gauss's law. Divergence of E equals to rho by epsilon naught. Rho is the charge density. So applying this relation, we may write rho equals to epsilon naught divergence of E. Putting the value of divergence of E, this is the E vector. Divergence of this plus divergence of this. Let us separate these two vectors. Now here, look at this expression. Divergence of this is vector, this is scalar. Divergence of this is vector, this is scalar. To find out this value, we should apply this vector identity. That is divergence of phi a. Phi is a scalar, a is a vector. The relation is grad phi dot a plus phi divergence a. So this is the vector identity relation. Phi is a scalar, a is a vector. So here this r vector may be treated as this a vector and this scalar portion may be treated as this phi. So applying this vector identity over here, divergence of, let us find out the value of divergence of r vector by lambda r square e to the power minus r by lambda. This is the scalar, this is vector. So using this relation, we may simplify this expression. And after that, finally, we'll get this relation. So this is the final form of that expression. Plus of this, minus of this. Similarly, the second term, divergence of r vector into this scalar, applying the same relation, divergence of phi a. So this is our phi, this is our a vector. So after simplification, we get this relation, the expression. So we have calculated separately the expression of this value and the expression of this value. Now let us put the values of divergence of this and divergence of this in this original expression, that is the equation 1. So finally, putting the values of all the estimated values in the original expression, the value of rho is found to be this one. So this is the expression of charge density. Now it is clear. So that type of problem may be coming in the exam, semester exam, and you may solve this problem using this methodology. Let us consider second problem. Electric potential in a charge-free space or medium is given by V equals to x square plus y square minus z square. It is given. Calculate charge density. So what formula you have to apply to solve this problem? Poisson's equation. Del square V, V is a scalar potential, equals to minus rho by epsilon naught. This is the Poisson's relation or Poisson's equation. So applying this Poisson's equation, let us first find out del square V. Simple vector relation. Applying the formula of del square V, we have calculated the value of del square V, that is 2. So putting this value 2 over here, the value of rho is found to be minus 2 epsilon naught. So this is another type of problem. So rho or charge density is found to be minus 2 epsilon naught. You may consider its mod value also. Now consider the third problem. that is a rectangular loop of each side. So this is a rectangular loop. This side is of 8 centimeter length. This is of 2 centimeter length. It is placed in the external magnetic field B. The value of B is given. You have to calculate the induced current. So the loop is placed in the external magnetic field and suddenly it is pulled out or it is pushing. So flux should be linked with this loop. Therefore induced EMF should be associated. Therefore induced current should be associated with this loop, and you have to calculate the value of induced current. That is the problem. You may read the problem. It is written over here. So here induced EMF, this is the formula of induced EMF from Faraday's law of electromagnetic induction. So epsilon induced EMF equals to d phi by dt, dt of BA. B is the magnetic field, A is the area for fixed. This is the relation B phi equals to surface integral B dot ds. But here for fixed volume and fixed magnetic field B into A, B depends on T, A doesn't. That's why it can be written as A dV dt. Put in the value of A and dV dt, that is given 0.02 Tesla per second. Put in the value of all these parameters. The value of induced EMF is found to be 3.2 10 to the minus 5 volt. So the induced current can be calculated from this relation induced EMF by resistance. Resistance is given 1.6 ohm. So its value is found to be 2 10 to the power minus 5 ampere. That is the expression of induced current. The next problem, that is a problem 4. In this problem, two circular loop placed at a distance of suitable distance is given at a distance of 5 millimeter. Cross sectional area of the loop is also given. You have to calculate the displacement current. Inside the loop, the place is air media. It acts as a parallel plate capacitor. So the current developed over here, that is the displacement current, you have to calculate the expression of displacement current. So first of all, let us calculate capacitance of this capacitor using this parallel plate capacitor formula, epsilon naught A by D. Put in the values of all these variables. The C is found to be 5.56 10 to the power minus 11 farad. So by the given condition, I equals to dq by dt. I means dq by dt. Q equals to C into V. You know the relation between charge, capacitance and voltage. C dV dt. It is given this current, charging current, that may be treated as conduction current, equals to 0.2 ampere. So dV dt can be calculated as 0.2 by C, that is the 3.6 10 to the power 11 volt second inverse. So the displacement current is found to be ID equals to C dV dt. That is the formula of displacement current. Actually this is the displacement current density 1 by A dq prime by dt. That is Q prime equals to C into V. So C by A, this is the displacement current density. So displacement current means JD into A. That is the displacement current. So C dV dt means from this relation, C dV dt means 0.2. So displacement current is found to be 0.2 ampere. So it is clear that displacement current and conduction current has a same value. Next problem, problem number 5, that is also very important problem. A square loop is placed in a magnetic field. It is suddenly pulled out. Calculate the work done in this process. Its length is calculated to be this one. Area is given. Velocity can be calculated from this expression. So induced EMF, this is the formula. So from this expression, dimensionally this is the induced EMF. It is found to be 0.1 volt. So induced current may be calculated, the induced EMF divided by resistance. This is the expression of induced current. So applying the relation, that is the force acting on a current carrying conductor, that is I dl cross B, integration dl cross B for a fixed conductor, I into L into B. So this force is estimated to be 2 × 10⁻⁵ Newton. So it is acting on the left side. So same amount of force has to be applied to pull out this square loop. And this is the length, is the displacement. So the work done can be calculated from this relation. This force that is applied to pull out the loop, square loop from the magnetic field into its length, and it is found to be 1 × 10⁻⁶ Joule.